This is a topic that I've often thought about, and these videos are really more for me than they are for you. Um, but, just a little bit of backstory. Algebraic geometry, I always thought that the algebraic geometers were kind of gods of math because so much of what they do seems so esoteric. And I was always very intimidated by this topic because of that fact, and I decided I wanted to kind of share what I've learned and really record it for myself in the simplest form possible. And so none of these explanations or ideas are really my own, but um, I'm just going to spit out some of the easiest methods of understanding these topics that I've found to date. This is actually a demonstration of a pre-sheaf, what I've drawn here. So I won't actually define this idea until later on, but there's aspects about this that I think are important to get out of the way before going into any of the zero sets or anything like that. So what I've drawn here are three functions, f, g, and h. Now, these are differentiable in certain parts of this big domain U, okay? And so if I define f of u to represent of these three functions, which ones are differentiable on u. So f, think of it as being which functions are differentiable. I can say that the only one that is differentiable on all of u is g. Similarly, I could say that f of v, a smaller domain, I could see that f is differentiable as well as g, but h still isn't differentiable. So now I have f and g. And then finally, for the smallest domain, I have all three functions, f, g, and h. Now what I want you to realize here is what we call the reverse inclusion. You'll run into this over and over and over again in algebraic geometry. So here I've just said that U contains V and V contains W, right? W is clearly inside of V, V is clearly inside of U. And what does that mean for the differentiable functions that live on those subsets? Well, it means that there's a reversal of these inclusions. Okay, so notice that it's going one way and the little caps, the subset ofs, are facing one direction here. And then I've ordered u, v, and w down here the same way, but I have to reverse the order of these subset ofs. So in other words, the bigger the set gets, the more restrictive it is. The smaller the set gets, the less restrictive it is. Therefore, it has more elements inside of it. And this, again, is called the reverse inclusion. Reverse inclusion. Another cool name for it is contravariant functor. Now, I haven't given enough to really explain what that means, or what a sheaf means, or even really what a pre-sheaf means, but this idea of reverse inclusion will occur throughout the topic of algebraic geometry very repeatedly. Very repeatedly. I should just say repeatedly, I guess. It's not really a... Anyway, so yeah, let's continue. Now, the next thing we'll need to understand is the definition of a ring. If you're watching this, you should know what a ring is. If you don't know what a ring is, stop watching this. A ring is just an abelian group under addition that's closed under multiplication. The classic example is z. Z, the integers. The integers are obviously closed under multiplication, and they are an abelian group under addition. Now, the fact that they're an abelian group under addition means that 0 has to be included in this ring. We're going to be looking at special rings called commutative rings. With an identity. Okay, so that means 1 is also included, just like the integers. And in the integers, similarly, multiplication is commutative. In other words, if I take two integers, say 2 and 3, and I multiply them together. 2 times 3 is the same as 3 times 2. That's all we mean by commutative. The next thing we want to look at is subgroups of A, and those subgroups are called ideals. These ideals are closed under multiplication. A good example of an ideal is 6z. This is just 0 plus or minus 6 plus or minus 12, etc. All the multiples of 6. The next thing we want to consider are special ideals, like prime ideals. A prime ideal is just an ideal, but if we have some element of I that's a product of two elements in the ring, A times B, that implies that A or B has to be an I. An example of this is 3z, right? That's a prime number. That's why we call these prime ideals. 3z, again, is just 0 plus or minus 3 plus or minus 6, etc. But if we look at 6, which is the product of 3 and 2, what this implies as being a prime ideal is that either 3 or 2 needs to be in the ideal. And as we see, 3 is clearly in the ideal. So this is a prime ideal. It's non-trivial to prove that something is a prime ideal, but it's usually not that difficult, especially with the integers. An ideal called a maximal ideal is the largest proper ideal possible. In other words, it's not contained in a larger proper ideal. Another example of this here is like a prime number times z. I'll pick 2z. We know what that is. It's just the even numbers. It's the evens, okay? This is maximal because if I include even one more element in 2z, I've included an odd number. And then I can get 1, which means it's the entire ring. Now, there's a cool property to maximal ideals. If I take the ring A and I mod out by a maximal ideal, I get a field. That's because fields are rings that don't have any ideals, have any proper ideals, I should say. What that means is that, and because of that, because this is maximal, if I mod out by it, there's nothing in between the two, so I don't have any proper ideals, which means I get a field. Similarly, if I take a prime ideal and I mod out by it, I get what's called an integral domain. Meaning I get something that doesn't have any zero divisors. Both of these things are going to come up useful here in a minute. Another example of a ring, which we'll be using quite extensively, is the ring of polynomials within variables. So here I have n equal to 3. This is the ring of polynomials for some field k. Now, if we're looking for ideals in this ring, one ideal might be x1 minus 3. Okay, the ideal generated by polynomials that have x1 minus 3 as a factor. Okay? Oops. And maybe we take just a second to sort of convince ourselves of this. This ideal is basically going to be the set of all polynomials x1, x2, x3 times x1 minus 3, where P is in this ring I put up here, and I'll call it A so I don't have to keep writing. So if I multiply, this by anything in the ring, I still have this factor. If I subtract any two of these elements, I still have this factor. If I add, I still have this factor, etc., etc. And of course, notice that 0 is in this ideal. 0 is in all ideals, okay? 0 is always an element of the ideal. Another thing to note is that if you're trying to prove things about this, what the fuck is this? Oh shit. So, another thing to think about is that if you have 1, if you ever have an ideal with 1 in the ideal, you have the whole ring. That's a concept that will come up in the future. Okay, I think we're ready to get going. So I'm going to stop this video and join me for the next one.